Hello, y'all. Barry Jr. here, back with some more physics as promised, some graduate level of classical mechanics, a bit later than normal on a Saturday or whatever, but of course, sort of an impromptu session. Wearing my shirt from my community college where I got two associate degrees, summa cum laude. So I'm a Palo Alto alumni, which is not in California. A lot of people think that is in Texas. So what I'm going to do is do one problem, which is going to be problem from chapter one, number 19 in Classical Mechanics by Goldstein, Poole, and Safko, the book that you saw on the intro screen. So I'm going to obtain the Lagrange equations of motion for a spherical pendulum, i.e. a mass point suspended by a rigid weightless rod. And I'm going to actually be utilizing the solutions to make sure I get everything correct in preparation for the exam this week. So we'll go ahead and get started. I'll do this one problem. I'll probably be back tomorrow for another problem. So looking at the drawing, we have the z-axis and the pendulum here, the bob at the end. So the forces that we have going on here, situate my screen a bit. We have the length of the pendulum, which of course for a big part. We'll call this L. We have, this is the mass. We have this angle here is theta. Um, she also has a displacement from the x-axis. I'm not sure exactly why. We shall go with it. So do it should just turn this sideways. So we have okay, the x-axis, the y-axis, and the z-axis. It's anchored there. So we're using physics coordinates. So in the xy plane, this is phi. I guess let's just say this is phi. Theta is how far away it is from the z-axis. Phi is how far it is from the x-axis. And we're going to use the Lagrange without multipliers. Maybe I should try this problem with multipliers as well. Uh, but I see we're doing the constraints. So one thing that we know is that L is fixed. So x squared plus y squared plus z squared equals L squared, or which equals r squared if we put this in spherical coordinates. So using this one constraint. Like it can move, let's say that this pendulum can move in all three dimensions wherever we move it, except for the fact that the the string stays the same length. That's the constraint. So we basically have uh, 3n minus k degrees of freedom. So it's 3 times one particle minus one constraint. So it's 2 degrees of freedom for this particle to move left to right, up and down. So for generalized coordinates, um, we opted to use theta and phi, which makes sense. And actually, hold up, it means it could still move in 3 dimensions because phi can still change according to this. So it can still move in 3 dimensions, but it does have the constraint that wherever it moves in 3 dimensions, L will be the same. So Qi equals theta and phi. Those are our generalized coordinates. So kinetic energy equals 1/2 mx dot squared y dot squared v dot squared. And using spherical coordinates, x equals L, since that is the actual length, cosine phi sine theta. Y equals L sine phi sine theta. V equals L cosine theta. So checking out I see. Is because that is x dot squared, not x squared. So I have to do x dot equals, L is not going to change, that's constant. But phi may change. So there's negative L sine phi sine theta plus L cosine phi cosine theta. Using the chain rule, y dot equals L cosine phi sine theta plus L sine phi cosine theta, and z dot equals L negative L sine theta. Oh crap, hold up, theta changes and phi changes. We have L cosine theta phi dot and theta dot phi dot theta dot, and then we have theta dot. So let's see if I got this correct. Looks like I did. So we just have to remember to take the derivative of both phi and theta, since they are if they change as well. Hey, what's going on, Fredo? I'm glad you're enjoying. Thanks for dropping a line. I'll forget seeing you as well. Let me know if you have any questions or comments. I'll be happy to reply. And right now I'm doing a pendulum, a 3-dimensional pendulum, suspended by a bob, and I'm getting the Lagrange equations for those. So I'll do one problem tonight. I'll probably come back tomorrow for another problem, hopefully earlier. I'm already sleepy. I want to make sure I popped in, since I said I would. And I'll do the same thing tomorrow as well, but I'll focus on being here earlier. Thanks again. Good seeing you, Wilfredo. So now we have this, and the main thing here is to get the derivatives right. Uh, then we can take and square them. So it'll just be all of that squared. Y. Basically, all I have to do is just copy all of this and literally square each of these. What I'll do rather than actually working these out, like manually squaring these, I'll just go ahead and follow up with the solutions on these. So suffice it to say, after I square all of these and add them all together, the professor's pretty good at that. She did it in one go, but of course she's a PhD, so makes sense. But I square all of these. The off values should cancel in the end. I've done this once before. It's just tedious. But you just square everything cancels out. And let's just know that after I square everything and cancel everything out and plug everything in, I have kinetic energy and spherical coordinates is 1/2 L squared theta dot squared plus L squared phi dot squared sine squared theta. So now we have the potential energy of the three-dimensional pendulum here taken from Cartesian coordinates, the kinetic energy, into spherical with two generalized coordinates theta and phi, which can each change, right? So then we need the potential energy to get the Lagrangian. So looking at the pendulum, we have this height here for the pendulum. And we know generally potential is mgh, the mass of the particle, gravity, and how high it is, how high it has to fall. So what we need to do now is put h in, and actually, sorry, h will be here. We need to put h in terms of the variables that we have. This is h. So looking at this, we can see that this height, this distance here, is going to be L cosine theta. So I can say L minus h equals L cosine theta. So if I put h on the other side to make it positive, L minus L cosine theta equals h. Let me know if you have any questions about how I did that. So basically, I want to know how high the pendulum is from the ground. I'll call this potential energy zero. Like if it's at zero, it's just bright, almost scratching against the ground, let's say. And let's say there's even a little moat dug out for it. So the pendulum sort of drags through that little moat, but it doesn't really touch it. But the center of the pendulum is at ground level, it has zero potential energy. And we know the length of the entire pendulum bob. So we know that the full length, the very full length of L minus this distance from the top to where it's at is how high it is. We have the full distance minus the distance to, minus what's not in that distance. is this distance here. So the full distance minus this distance that's not how high it is equals how high it is. And that's how we get to this right there. So we can say V equals mg L minus L cosine theta. And the professor looks like she has that. She has mg L cosine theta, not the L minus. So let me think about that. L cosine theta is this part right here. Hmm. Typo? Pretty sure it should be L minus L cosine theta. In other words, this full height, like I was saying earlier, minus the the height above where it's at gives us the height where it's at. So it's full height minus the height where it's not above where it's at gives us the height where it's at. I'm going to use this and see if I get the same answer. Does that understand that? So using this, I'll say V equals mg L 1 minus cosine theta is extracting out the L from the 1 minus cosine theta. Right? Lagrangian is going to be T minus V. So it's going to be 1/2 m L squared theta dot squared plus L squared phi dot squared sine squared theta minus mgl 1 minus cosine theta. That's our Lagrangian. So now since we have our Lagrangian, we can get the equations of motion by applying the early Lagrange equation to each specific coordinate generalized. So we have d dt partial L over partial theta dot minus partial L over partial theta equals 0. So partial L over partial theta dot equals 1/2 m 2L squared theta dot equals m L squared theta dot. The full derivative dt partial L over partial theta dot equals m L squared theta double dot, since L doesn't change, m doesn't change. So we have the equation of motion is going to be, oh, I have to get the other part, partial L over partial theta equals L squared phi dot squared 2 sine theta cosine theta, using the chain rule on this part. Oh, and I have to still do 1/2 m. I'll just put m over 2, because m over 2, the 1/2 m will distribute to the whole thing. So 1/2 m L squared phi squared 2 sine theta cosine theta, which equals m L squared phi dot squared sine theta cosine theta. So I have plugging these things in. I have ml squared theta double dot minus ml squared phi dot squared sine theta cosine theta equals 0. Let's see if I have that correct. L squared squared. I'm sorry, doing phi. I'm looking at the wrong part. Ml squared theta dot squared. I did forget this part over here for my theta. So this part, I got the first theta, but I didn't get the second theta. I have to not miss thetas. So I have minus MVL, and this is going to distribute. Minus is going to make it plus. These negative here. There's already a minus there, which I have. So that minus is taken care of. Now I have to distribute this minus to the cosine and makes it positive. Then I have to take the derivative of a cosine that makes it negative sine theta. Yep, it looks like that's right. So we have that NGO sine theta. And it looks like she used a trigonometric simplification on that part with the sine theta, cosine theta. I'll see if I can do without that. Hopefully I can. Equals 0. Say, and I can actually copy this down. I'll solve for theta double dot. Theta double dot equals that plus that divide that to the other side. That makes all of that positive. So that equals phi dot squared sine theta cosine theta plus sine theta over g sine theta over L. Looks like I messed up my negatives here. That makes it positive. I'm going to take the derivative. That makes it negative. Oh, I have to subtract the whole thing. I have to subtract the whole thing when I subtract the second part. That's what I missed. Bring it to the other side. This does have a negative on it. Right, you have to watch out for these negatives. V over L sine theta is going to be negative, and pi is 5 squared over 2 sine theta, sine 2 theta. Let's use an identity. I'll just keep it the way it is. All right, so there's one equation of motion. Theta makes it for phi. We have the same thing. I'll just write it over here. d dt partial L over partial phi dot minus partial L over partial phi equals 0. So partial L over partial phi dot equals, maybe I should copy the Lagrangian down. I keep scrolling this much. So we have 1 half m. I've been willing to distribute that. To 1 dot phi dot squared theta. I'm taking the derivative of phi dot. d dt of that equals 1 half m. So this one makes it a more complicated because I have a sine squared theta of theta is a function of t. So I have to do this. I would say 2L squared phi double dot sine squared theta plus 2 squared phi dot 2 sine theta theta dot. I'm not sure if that's right. Let me see. Use a shortcut here. So, I mean, it looks right. I'll show you what I mean. Partial L partial phi equals, so there is no, scroll it down. There is no phi up in there. So that equals 0. So that means d dt partial L over partial phi dot minus 0 equals 0. So d dt of this equals 0. Thus, what you're saying is m L squared, if I multiply the 2 in, m L squared phi dot sine squared theta equals c equals a constant. So phi equals constant over ml squared over ml squared in sine squared theta, right? second derivative equals 0, according to this. So there's no need to even do the derivative. It's going to be constant. So now it looks like I have the equations of the motion. If as far as we needed to go for this problem, we have theta double dot squared and phi dot squared. So uh, phi doesn't seem to have any acceleration, which makes sense. There's no force moving it. Just not mention that there's an external force. So if it is spinning on its z-axis, around its z-axis, it'll be constant. There's no force affecting it. And but theta is changing because when it reaches its apex of its swing, it stops, then it speeds up. When it reaches the bottom of its swing, it's going as fast as possible. 100% of the energy is kinetic energy, 0 potential energy, and it slows down as it goes up. So the theta is constantly changing. And welcome who's joined. Be sure to drop a line, like and subscribe if you haven't. So the theta is not changing because it's in the x plane. If it's going around in a certain speed, if somebody gives that pendulum a spin, it'll just keep on spinning at that speed, according to Newton's first law. And the pendulum, the acceleration is happening over and over again as it slows down and speeds up. So that's why phi does have a double dot, because that's why theta does have a double dot. Mixing up my verbiage. Theta does have a double dot because it slows down and speeds up. But phi does not, because there's no force in the azimuthal direction. So those are the equations of motion. That's an example of using Lagrange equations to get equations of motion for a three-dimensional pendulum. And I'll be back tomorrow to do another problem or two, maybe multiple. I'll just be sure to start earlier. So be sure to be back tomorrow. I can't be sure about what time. I guess I will say 9 o'clock. But it may be a bit later, but I'll set a stream. I'll schedule one for 9 and work out from there. So thank you for joining, Wilfredo. Thank you everybody else who joined. I do hope you have a nice evening. I'll see you tomorrow.